Hi everybody, I hope this video finds you well. In today's video, we're going to be continuing on with our investigation of descriptive statistics for quantitative variables. To start off with, let's quickly summarize what we discussed from the last lecture. We, in the last lecture, talked about that there are sort of three main things that we wanted to measure when working with a quantitative data set. We want to understand the center, the variability, and the shape of that data set. In the last lecture, we managed to put together a couple measures of center as well as three measures of variability. So let's remind ourselves about those and some of the details that we found. So our first measure of center was what we called the mean or the average. In terms of notation, we often use the Greek letter mu when we're talking about the average of a population, and x with a bar over it when we're talking about the mean or average of a sample. Remember that the mean or average is what we consider a non-resistant measure of center. All that means is that if we have some extreme values in our data set, the mean or average will be affected by those extreme values. In other words, if there are some values that are much larger than all the others, the mean or average will be pulled towards those larger values. If there are a few values that are much smaller than the rest of the data, then the mean or average will be pulled to those lower values. Just something that we have to be concerned about and be aware of whenever we have extreme values in our data set. The second measure of center that we discussed was the median. The median has one notation. We always just write it as a capital M. And remember that the median was introduced to show us a resistant measure of center. Even if we have extreme values in our data set, the median will not be greatly impacted by those extreme values. We also discussed three measures of variability. The first, which was very basic, was called the range. Remember, the range is just simply the maximum minus the minimum. It's not particularly interesting, and it is certainly not resistant, but it is something we at least have mentioned, so we should remind ourselves of it. The second one, which was very important, was the standard deviation. Remember that when we write it with a lowercase sigma, that means that we're talking about the standard deviation of a population, and a lowercase s means that we're talking about the standard deviation for a sample. Remember that unlike mean and average, where there's just two different notations, but you calculate it the same way, population standard deviation and sample standard deviation are actually different values. In the previous video, where we sort of discussed how to use our calculator to calculate these basic statistical measures, we saw that the calculator does give you both the population and sample standard deviation. All that means that you need to do is make sure you're careful on identifying which standard deviation you need to use. Remember, though, that in statistics, more often than not, we have a sample, because generally in statistics we do not have access to the entire population. It's usually too large to study everyone in a given population. So 90-95% of the time we are working with a sample, which means if you're ever unsure, you should probably err on the side of using the sample standard deviation. Remember that the standard deviation measures how spread out or variable your data is based on the mean, which means that it is also not resistant. The third and final measure of variability that we introduced in the previous video was the interquartile range. Remember that the interquartile range is written as the IQR. It measures the difference between Q3 and Q1. So the interquartile range is a resistant measure of variability. It basically tells us how spread out is the middle 50% of our data. Similar to this interquartile range, we also discussed something called the 5-number summary of a dataset. Remember, the 5-number summary is just a quick way of summarizing a dataset. It has the minimum, the first quartile, the median or second quartile, the third quartile, and the maximum. Those 5 numbers make up what we call the 5-number summary. All right, so before we get into starting to talk about measures of shape and start learning how to visualize quantitative data, I'd like to do one more example helping us sort of have a better understanding of some of the main measures we're going to be using, especially standard deviation, because if you remember back from the previous video, we didn't get a chance to actually do any examples of standard deviation because it's a computation we want to use the calculator on. Now that we're sort of comfortable using the calculator, I'd like to look at least one example of helping us better understand standard deviation, as well as get a little additional practice using the calculator. So let's go ahead and take a look at a quick example. So for this example, we're going to consider the following 3 sample data sets. So data set 1 are the data points 48, 49, 53, 54, and 58. Data set 2 is 100, 100, 100, 100, 100. And data set 3 is 0, 9, 16, 23, 31. What we're going to do is we're going to do 2 things here. We're going to try to order these data sets from lowest to highest in terms of average, and then we're going to order these data sets from lowest to highest in terms of standard deviation. So this should be very straightforward by using our calculator. But before we do that, I'd like to make a little prediction. We should be able to sort of use our sense of what these measures are really attempting to measure to basically know ahead of time how these questions should be answered. In other words, what order these data sets should have based on the average or the standard deviation. So let's make a little prediction for part A. So again, we're not going to do any computation. Let's just try to make a prediction. Remember that the average is attempting to measure the sort of center or what is a typical value here. If we think about that, what is going to have the lowest average? Well, again, we're in a moment, we'll actually compute this, but keep in mind that average is measuring the center. So it looks like the typical values here are in like the 10s and 20s. The typical values here are in the high 40s, low 50s, and the typical value here is like 100. So we should be able to make a prediction for A that it's going to be data set 3 that is smallest, then data set 1, and then data set 2 in terms of average. If average is really measuring the center, then the center of this data set should be the smallest, the center of this data set should be sort of in the middle, and the center of this data set should be the largest. Let's see if we can do a similar prediction for B. So the prediction for B, remember, we're again trying to go from low to high in terms of standard deviation. What does standard deviation measure? Well, it measures how spread out your data is. So a small standard deviation means the data really isn't spread out, and a large standard deviation means that it is very spread out. So if we look at these, which of these has the least spread out data? Well, it should be very clear that data set 2 doesn't really have any variation. So we should certainly expect that data set 2 should have the smallest standard deviation. We might be even able to guess the standard deviation without calculating it. Like we just said, there literally is no deviation. So we would expect that the standard deviation for data set 2 should be 0. The smallest a standard deviation can possibly be is 0. And that means there is literally no variability in your data. All right, what do we think in terms of the next smallest standard deviation? Well, these numbers are clumped up pretty close to each other. They're not exactly the same number, but this one's only off by 1, then off by 4, 1, 4. Yeah, they all seem pretty close to each other. Whereas these, there's quite a lot of spacing. There's a gap of 9, and then of 7, and then of 7, and then of 8. They look a lot more spread out. So we might think that data set 1 is going to have the next lowest standard deviation, and data set 3 seems like it should probably have the largest standard deviation. Now, do we know what those standard deviations are? Well, no. Until we use the calculator, we won't be able to actually know the value of the standard deviation, but at least we have these predictions. Okay, so let's actually calculate this and confirm this. So we're going to make a little table here. So here's our data set, whichever one we're working on. So 1, 2, and 3. And then we'll make sort of what is its mean and what is its standard deviation. Now you'll notice that I'm using the notation for sample average and sample standard deviation. And again, that's just because it says that it is a sample data set. So it's going to be a data set that represents only a sample of whatever the population is. All right, so how do we do this? Well, first thing we'll need to do is we'll take this data and put it into our calculator. So if you're following along on your own calculator, make sure you go ahead and hit Stat, then Edit. If you have data already in list 1, you'll want to go up to where it says L1, hit Clear, and hit Enter to clear out everything in list 1, and then go ahead and type in the 48, hit Enter, then 49, hit Enter, 53, 54, and 58. Once you do that, you should have 5 data points in there. Once your data is entered in, you can go ahead and hit Stat, Calc, and then 1 var stats. If you have one of the newer calculators, 84 plus and beyond, make sure that your frequency list is blank and make sure next to list it says L1 because that's where we put our data. And then you can go ahead and hit calculate. If you have an older calculator, all you need to do is hit enter again and it should calculate everything. If you're a little unsure about the calculator aspect of this, go ahead and go back to the sort of calculator demonstration video where I actually have the calculator on screen so you can sort of see that. However, to confirm that you're doing this sort of correctly, you should find that the average for data set 1 is 52.4. Notice that does seem to make sense given the numbers there. 52.4 does seem like it's sort of in the middle. And then the standard deviation, remember we want the sample standard deviation, so we would use the SX on our calculator, and it looks like it should be about 4.04. You might ask, why am I only keeping 1 decimal place here and 2 decimal places here? Well, again, that's because the 52 is a larger number, so keeping only 1 decimal seems to make sense, whereas 4 is a much smaller number, so I'm keeping 2 decimals to be a little bit more accurate. Again, as long as you're sort of careful with your rounding, the amount of decimal places you keep in this class really is not a big concern. All right, let's go ahead and do data set 2. So we'll go ahead and hit Stat and Edit, and we'll clear out what's in L1, and we'll go ahead and type in our data set 2, which is 100, 100, 100, 100, and 100. Then we'll hit Stat and Calc and 1var stats again, and we'll go through and calculate. Unsurprisingly, we find that the average here is 100, and the standard deviation, notice both for sample and population, is 0, as predicted. So we can already see that this prediction has come true. Dataset 2 does indeed have 0 standard deviation. All right, finally, let's move to dataset 3. So again, we'll hit Stat and Edit. We'll clear out what's currently in list 1, and then we'll go ahead and put in 0, 9, 16, 23, and 31. Then Stat, Calc, 1var stats, one more time, hit Calculate, and we should find an average of 15.8 and a standard deviation, again making sure that we use the sample, of 12.03. So are our predictions correct? Well, let's look at, in terms of ordering these from the lowest to highest in terms of average. The lowest average is 15.8, then 52.4, then 100. So this prediction here, absolutely correct. All right, let's think about the standard deviation. Lowest standard deviation was indeed dataset 2, then dataset 1, and then dataset 3, which had the highest standard deviation. So there we go. So what this is really supposed to be doing is really 2 purposes. The first purpose is just to make sure, again, another example of making sure you guys are comfortable taking data, putting it through your calculator, and getting these statistical measures, in this case, average and standard deviation. More importantly, though, this is to really reinforce that average and standard deviation really measure what we want them to measure. Right? These averages here really do seem to indicate what a typical or middle value of the data set is, and these standard deviations really do measure how spread out the data is. The lowest a standard deviation can be is 0, which means there is no deviation present in the data. A small standard deviation means that the data, there is some variability, there is some spread, but there's not much. Whereas a larger standard deviation means that the data is actually quite spread out. You can also think about standard deviation as like a measure of consistency. Dataset 2 is a tremendous amount of consistency because all the numbers are the same. It has a very low standard deviation. Whereas dataset 3 has a high level of inconsistency because it has a high standard deviation. All right, now let's turn our attention to talking about the third attribute of quantitative data that we wanted to study, which was the shape of a quantitative variable. This means we need to start talking about visual displays. So let's introduce our first visual display. Eventually, we'll learn 3 different ways to visually display quantitative data, but let's start with our first one. So in terms of measuring shape, we will always measure the shape of a quantitative data set by building a visual display. The first visual display that we'll introduce in this video is what's called a histogram. In later videos, we'll talk about what's called a stem and leaf plot, or sometimes just a stem plot, as well as what's called a box plot. For now, though, let's talk about a histogram. A histogram is a visualization of quantitative data. So again, histogram is exclusively used for quantitative data. Just like bar graphs and pie charts are exclusively used for categorical data, a histogram is exclusively used for quantitative data. To build a histogram, we first create intervals that are each of the same size. We call these intervals classes. We then count the number of data points that fall into each class. So we basically make some intervals, some ranges of numbers, and then we count how many data points fall into each of those intervals. This gives us the frequency for each class. Then we draw our graph with the vertical axis being the frequency, so very similar to a bar graph, and the horizontal axis being our variable. And we label the horizontal axis by the ends of those intervals or classes. Since one class will end where the next one begins, the bars of a histogram touch. Remember back when we introduced a bar graph, we said that the bars should not touch, and this is the reason why. In a quantitative display, a histogram, the bars touch. That shows the viewer, oh, this is a quantitative variable. In a categorical visual display, a bar graph, the bars do not touch. So this helps us distinguish a bar graph from a histogram. Okay, in a moment, we'll actually take a look at an example of building one of these histograms from scratch. For now, though, let's talk about what we're actually looking for. I mean, if the idea of building a visual display is to measure the shape, we should probably get some words or terms for the shapes we're looking for. So, 4 shapes or distributions for quantitative data. So again, in our class, this is a survey class, so we try to boil things down to sort of the key components. We're not saying that this is true in every situation, but again, we're trying to give you guys just an introduction to these things. So when classifying the shape or distribution of a quantitative data set, we will be choosing for our class from 4 distributions. There are obviously far more than 4 distributions in statistics. There are even data sets that don't really have a well-defined distribution. But in our class, if you're ever asked what is the shape or what is the distribution of a data set, then you know it will be one of these 4 things we're about to talk about. So what are the 4 shapes or distributions that we'll run into? Well, the first is something that looks like this. If this is your histogram, so this is your frequency here, and this is your variable here, if you end up getting something like this, where you have very tall bars over here, and they get maybe shorter and shorter, and look something like this, you'll notice that this forms a tail off to the right. Now keep in mind this is going to be the variable, so this is always going to be low values here, high values here. So if you have a tail that's going off to the right there, we will call this a right skewed distribution, or a right skewed shape. So if we see something like this, we call this right skewed. There's of course a sort of reverse of this, the other way. So if when you're drawing your histogram, you end up with something where you have very tall bars over here, and then they get sort of shorter as you go this way. Then this, again, where this is the frequency and this is the variable, you'll notice that now we would sort of view the tail as going this way to the left. So we would call this a left skewed distribution. So right skewed and left skewed basically have tails that go in that direction. So in a right skewed distribution, you have a tail that goes to the right. In a left skewed distribution, you have a tail that goes to the left. The next 2 types of shapes that we're going to talk about fall under sort of an umbrella category of what's called a symmetric distribution. So symmetric distributions. Okay. There's 2 types of symmetric distributions that we run into. The first, which is perhaps the most famous, if this is frequency and this is variable, are distributions where you have very tall bars in the middle, and then they get shorter in both directions. So something that looks like that. This is referenced as what's called a Bell or normal distribution. And we are going to study this type of distribution in a lot of depth, because normal distributions are one of the most important in statistics. Why are Bell or normal distributions called Bell or normal? Well, you can sort of imagine if you drew a curve over this, you're making sort of a bell shape. You can also see why it's called, in general, a symmetric distribution. If you sort of cut this in half, this side over here looks roughly the same as this side over here. That obviously is not the case for these here. If I cut this down the middle, what's over here does not look the same as what's over here. Cut this down the middle, what's here does not match what's here. But in this case, the 2 halves should be roughly the same. The other type of symmetric distribution that we will run into, though it is much sort of more rare, is if this is the frequency and this is the variable, is a distribution where the bars are all about the same height. So if you see something like this, where when you go to draw your histogram, all the bars are roughly the same height, then we will call this a uniform distribution. You can again see why this gets classified as a symmetric distribution. If you cut this down the middle, what's over here should roughly match what's over here. So Bell normal and uniform distributions are both symmetric distributions, but they are of course very different. In a bell shape, they are sort of two tails, one going each direction, whereas with a uniform, everything is about the same height. Okay, so if any time you guys are asked to describe the shape of a quantitative data set, it will, for our class, be one of these four shapes. So these are the four that you absolutely have to make sure you understand. All right, so I think this is enough for us to get into an example here. We should go ahead and actually build a histogram and try to diagnose its shape. All right, so for this example, we're going to suppose that a researcher is studying the hours per week that employees at these cheapo coffee shops work. So to study this, the researcher randomly selects 3 of these cheapo coffee shops and interviews all the employees at those shops. So they end up talking to 22 employees, obviously, because if there's 3 coffee shops, there's going to be several employees at each shop. So they ultimately talk to 22 employees, and they get the following data. Each of these data points, as it tells us here, is a value that is the hours worked per week. So one person said that they work 4 hours a week, somebody else said that they work 15, somebody else said that they work 55 hours per week. So we're going to do a bunch of things here, some as sort of review and some as sort of new content here. So we're going to do our classic identify the population, sample, and individual. We're going to talk about the sampling technique. We're going to calculate the mean and standard deviation. We're going to give the 5-number summary. We're going to calculate the range in IQR. And then in the very last bit here, we're going to construct a histogram starting from 4 with class size 8 for this data set, and then use this to describe the shape of the data set. All right, let's get in and talk about each of these pieces. So for the first part, our standard sort of diagnoses, we need to talk about the population, the sample, and the individual. Well, if we look at this, we can sort of see that if these are our sort of 22 data points, our sample must be 22. What were these individuals? Well, they were 22 of these employees. So our sample here were 22 employees of cheapo coffee shops. Well, that should make an individual very easy. It's just one employee. Again, we could say of cheapo coffee shops, but I think that's redundant. We can just say one employee there. And the population, well, it should be all the employees. Right? So all employees of cheapo coffee shops. And, just because it looks there, let's go ahead and just write it for all of them. Yeah. All right, so there we go. The population is every employee of a cheapo coffee shop. The sample is 22 employees that we ended up talking to after sampling 3 different coffee shops. And the individual, of course, is one employee. Again, remember that as our standard structure, population should be all of something, sample should be a specific amount of something, and individual should be that one building block of the population and sample. All right, let's talk about the sampling technique that was used here. So sampling technique. Well, remember for sampling techniques, we have 5 that we discussed in our class. That's the SRS, the systematic, the stratified, the cluster, and the convenient sample. Now, we can see here that it mentions randomly selecting, so we know things like convenience are out, and we also know systematic is out because in systematic you build a system rather than doing things randomly. So, which should this be? Well, we got to be a little careful here. It said we randomly selected 3 coffee shops, but notice we talked to 22 employees. So we selected 3 shops, but we were talking to 22 employees. That meant that every time we chose a shop, we added multiple individuals to our sample. That makes our sample a cluster sample because every coffee shop gave us several individuals for our sample. So our sampling technique here was cluster. And the clusters were the shops. We randomly selected 3 shops or 3 clusters and ended up with 22 individuals in our sample. All right, let's go ahead and calculate the mean and standard deviation. Of course, this is a sample, so we'll want to use the notation x bar and s. How are we going to do this? Do we need to do it by hand? Absolutely not. We want to just go ahead and put this data into our calculator. So if you're following along with your own calculator, you can hit Stat and Edit, clear out what we had from the previous example, and start typing this stuff in. So we've got 4, 5, 8, 10, 10, 10, 11, 12, 15, 15, 18, 18, 18, 20, 25, 25, 30, 32, 35, 40, 40, and 55. Since this had a lot of data, it's probably a good idea, put your cursor back on 55 when you type that in, and you should see that it says like L1 of 22 equals 55. That means that this was the 22nd data point we typed in. Now, could we have possibly made a typo? For sure, but we do at least know that we typed in 22 data points, so at least we know we didn't miss any data points or put in any extra ones. Let's go ahead and hit Stat, Calc, and then 1var stats, and we can hit Calculate. And we should get that our average here is approximately, we get 20 point, we'll keep 2 decimal places, 73. We should include units. Since everything was in hours, this would be in hours. So the average time worked per week is 20.73 hours. And the standard deviation, which we would use S because it is a sample, would be 13.21 hours. So there we go. There's the mean and standard deviation for this data set, and always make sure to include units, which in this case, of course, would be hours per week. Okay. Let's see what we got to do next. We want to give the 5-number summary. Remember, you can also get that from our calculator. So the 5-number summary, if we want to do that, that should include the minimum, Q1, the median, Q3, and the maximum. If you're still on your 1var stats from your calculator, you can scroll down a little bit, and you should see all those values. The minimum was 4, Q1 was 10, the median was 18, and Q3 was 30. The maximum was 55. All of those would be in the same units, hours. So the minimum somebody worked per week was 4 hours per week. The maximum was 55. The median was 18 hours. Notice that the mean and median do give us different ways of visualizing the center. And Q1 and Q3 were 10 or 30 hours, respectively. All right, I think we had one more thing that we'll do. We'll try to save this on this page here. We also wanted to calculate the range and IQR for the data set. So let's just do those here. This is just practicing all the major components. Range, remember range is maximum minus minimum. So all we would need to do for that is 55 minus 4, which is 51 hours. So there was a gap of 51 hours between the person who worked the lowest amount per week versus the person who worked the most per week. And the IQR, well, remember IQR is Q3 minus Q1, so that would be 30 minus 10, which equals 20 hours. So the middle 50% of our data is spread over a range of 20 hours. In one of the later videos about quantitative variables, we'll investigate a little bit further why we want the IQR. Right now, it's just something we want to make sure we're comfortable calculating, but it does serve an important purpose later on in our class. All right, let's go ahead now and turn to the visual display. So we'll go ahead and give ourselves the same data back, but we'll turn our attention to part F here. So when constructing a histogram in our class, you get some very important information. You'll notice that in the description of the problem, it says that we want to construct a histogram starting from 4 with class size 8. So this tells us how we're going to build those intervals or those classes. So to start off with, we're going to make a little table with our classes and the frequency. So how do we build these? Well, it tells us starting from 4. So our first interval is going to be from 4 with a class size of 8, meaning we should go 8 units in that direction. So it'll be 4 to 12. The next one is going to start off where this ended, so it'll be 12 to 20. Then, if we scoot down just a little bit, the next one should be 20 to 28. Notice that the gap is always by 8 because it says class size 8. And also keep in mind that where one ends, the next one starts because we're doing this quantitatively. So 28 and then 36. and then 36 and 42. That's looking pretty good. If we go back up to our data, we had somebody who was as high as 55, so we do need to go a little further. 42 to 50. We said the highest one was 55, so we will also need to include 50 to 58. Okay. Notice all of them have the exact same size of 8, and we started from 4 because that's what they told us to do. Now, we do need to remember one important idea about intervals back from algebra. When you learned about intervals in algebra, you probably learned about sort of a hard bracket and soft bracket notation. A hard bracket meant that it was included, and a soft bracket meant that it was excluded. And we do need to make use of these because otherwise, if we had a data point, say like 12, we have to decide, does it go into this one, 4 to 12, or does it go into this one, 12 to 20? So the convention for our class is that we will always include the left end and exclude the right end. So this interval includes 4 and goes all the way up to 12. So that would include things like 11.9, but it doesn't include 12. Then on this one, we'd put 12 included and 20 excluded. So if there was somebody who worked exactly 12 hours, they would land in this class, as would somebody who worked 19.9 hours. Somebody who worked 20 hours, though, would end up in the next one. So our convention is we're going to always include the left end and exclude the right end. All right, that's always how we're going to build these classes. All right, now we need to get the frequencies. How do we determine the frequencies? Well, we count. We have to count how many of the data points land in each of these classes. So let's look for the first one, 4 to 12. Remember, we should include 4, but not 12. So if we look here, we've got 1, 2, 3, 4, 5, 6, 7, because we're including 4, but we're not including 12. So all of these people would be in that first class. So I'll just put a little line there. There we go. We said that was 1, 2, 3, 4, 5, 6, 7. So the frequency for that first class would be 7. For 12 to 20, we should include 12 and go all the way up to, but not include 20. So that would be the 12, 15, 15, 18, 18, 18, but not the 20. So we would go up until right there. How many people is that, or how many individuals? It's 1, 2, 3, 4, 5, 6. So we have 6 as a frequency there. For 20 to 28, we do the same thing. That would be this, 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 but since it ends at 28, we would not include the 30. So there we go. That means that's going to have a frequency of 3. For 28 to 36, we would include this, 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 but not the 40. Since we're only going up to 36, that means it also has a frequency of 3. For 36 to 42, we would include these two, but not that one. So I guess we can imagine sort of there. That's going to be a frequency, like we said, of 2. For 42 to 50, well, that still doesn't include this one, so I guess if you want, you could imagine that there's sort of another line in there. Let's go ahead and make that just a little bit clearer. So there's a line and then another line. There we go. So remember, this guy was 2. That means the frequency here was 0. There were no data points between 42 and 50. And for 50 to 58, only that one data point, 55. So we'd have a frequency of 1. Should be no doubt what these frequencies sum up to if you want to do a quick check to make sure you didn't miscount anything. 7 plus 6 is 13, plus 3 is 16, plus 3 is 19, plus 2 is 21, plus 1 is 22. Of course, it has to add up to 22 because, well, we had 22 individuals in our sample. All right, now we can actually draw our histogram. So we'll draw coordinate axes here. So remember, this is going to be the frequency here. For the frequency, just like a bar graph, you need to start at 0 and then have some sort of consistent scale. So we could do something like 2, 4, 6, 8. I could have also just gone by 1s, but it'll be a little bit faster to go by 2s. And then for this will be our variable. So remember, this was the number of hours worked per week. And we want to label this axis according to these endpoints. So we can go ahead and start here. 4, 12, 20, 28, 36, 42, 50. I'll have to go a little bit further. 58. So again, these things here, it'll be guaranteed to be a consistent scale because each of these classes is the same size. Remember, the class size was always 8, so you'll notice that the gap here is always 8. All right, now we draw in some bars. Our first bar should go up to a height of 7, so that should be between 6 and 7. So there's our first one. The next one should go as a height of 6. Notice that the next one will touch because where one interval ends from 4 to 12, the next one starts from 12 to 20. Then from 20 to 28, we have a height of 3, so we have right there. Then another height of 3 right there. Then a height of 2 right there. Then we have a height of 0, so nothing there. And then we have a height of 1 right there. So this guy has a little gap there because there was nobody between the 42 and 50 mark. What is the point of this sort of histogram? Well, it's to tell us about the shape. Which shape would we sort of classify this as? Well, if we go back and take a look, we could see that the sort of shapes that we have choices between, right skewed, left skewed, bell normal, and uniform, very clear that this should be classified as a right skewed distribution. If we take a look again at our graph, we have this tail extending off to the right. So we would classify this as a shape as roughly right skewed. So there we go. There's our first example of constructing a histogram. Keep in mind a histogram is really sort of a two-step process. First, you have to create these classes and get their corresponding frequencies, and then you're able to actually draw the diagram. For our class, well, you don't have to sort of guess how to make these. You're always going to be told where to start and what size each interval should be. Okay. Now, at this point, we've sort of introduced our first visual display, and we've talked about the shapes that we're looking for. But we should probably talk a little bit more about what these shapes really mean. I mean, the fact that this is right skewed is nice. I mean, it does seem to go to the right. There's a tail to the right. But what does that really mean in terms of analyzing the data? Well, the first thing that we'd sort of like to point out here is that if we were just looking at the raw data, and we can certainly also see this from sort of the diagram, is that there were some sort of extreme values towards the end. Now, I don't know if I would consider 40 and 55 as extremely high values compared to the rest of the data, but they're certainly larger than the rest of the data. So the fact that this is right skewed is sort of telling us that there are some very high values in our data compared to the vast majority of the data. That actually ties in to the concept of mean and median. If we go back to where we calculated mean and median, it's actually not a coincidence that the mean was 20.7, whereas the median was only 18. The mean is a bit higher than the median in this situation because of the right skew. Because of the fact that there are a few much higher values than the rest of the data, the mean is pulled in that direction. And that's why we're seeing a mean that is larger than that median. That is actually a rule in general about the relationship between the shape of a distribution and the mean and median of the data set. So let's talk a little bit about that. So we're going to talk a little bit more about shapes and their relationship to mean and median. So a right skewed distribution, like the example we were just doing, means that most of the data is on the low side, but there are a few very high values in the data set. I mean, that's what a right skewed distribution means. And you've got some very tall bars over here for low values, and then you've got a few not so tall bars for higher values. So that means most of the data is on the low side, but there are a few very high values in the data set. In other words, a right skewed variable, if we figure out that a variable is right skewed, that means that low values of that variable are very common, whereas higher values are very rare. How does this tie in to mean and median? Well, in general, right skewed distributions, we will usually find the mean to be greater than the median. So if you ever want to sort of confirm that your choice of shape is correct, if you're going to say something is right skewed and you calculate the mean and the mean should be higher than the median. The exact reverse is true if we're talking about a left skewed distribution. A left skewed distribution means that most of the data is on the high side, but there are a few very low values in your data set. Visually, left skewed means that you have some very tall bars over here. That's high values of your data. And then you have some very small ones over here. That's for lower values, so low and high. So, in other words, a left skewed variable is one where the high values of the variable are very common and low values are rarer. because there are going to be some very extreme low values in a left-skewed data set, that we expect that in a left-skewed distribution, we will find that the mean is less than the median. All right, what about in those symmetric distributions? Well, a Bell normal distribution means that most of the data is in the middle, but there are a few very high and very low values in the data set. So Bell normal means that you've got sort of tall bars in the middle, and then they get progressively smaller on both sides. So most individuals are here in the middle. There's a few that are much lower. There are a few that are much higher. So in other words, a Bell normal variable is one where both really low and really high values are rare. In a Bell normal distribution, since it's symmetric, since there isn't a tail pulling the mean in one way or the other, we will usually find that the mean is roughly equal to the median. Doesn't mean that they're exactly equal. Only in a perfectly symmetric distribution will they be exactly equal. But if your mean and median are pretty close to each other, that might mean that you're looking at something that's symmetric. Finally, a uniform distribution, if we think about what that meant that all the bars are basically the same height. Well, that means that low values, medium values, and high values of the variable are all equally likely. So it's just as likely that somebody has a very low value for that variable as it is that they have a very high value for that variable. In other words, uniform variables are one where all values of the variable are equally likely to occur. Now that's very different than what a Bell normal is, but they are both symmetric. So again, in a uniform distribution, we will usually find that the mean and the median are very similar to one another. All right, now I know that's a lot of information about all these different types of distributions, so let's crystallize this a bit with an actual example. We're going to take a look at a few quantitative variables, not with any data, but just the variables themselves, and sort of think about which of these distributions is the most likely. And the reason that we're going to do that is it'll really help you guys understand that the shape of a variable really means something about what that variable is telling us. So, for each of these sort of following quantitative variables, we're going to talk about number of children in a U.S. household, age of death in the United States, heights of adult males in the United States, and ages of students in a public high school. All of those are quantitative variables, right? If you think about recording the numbers, number of children would be like 0, 1, 2, 3, 4, 5, etc. Age of death would be, oh, that person died at 73, that person 68, that person 89. It would all be a quantitative value. Heights, same thing. That person is 65 inches. That person is 74 inches, so on and so forth. And same thing with ages in a public high school. That student is 14, that student is 15, so on and so forth. So certainly these are all quantitative variables. Because remember, shape and distribution is only a concept that applies to quantitative variables. So let's go ahead and try to think of what the most likely shape would be. Now, if we were going to do this in real life, we would of course collect the data and then analyze the data just like we did by building like a histogram. But I'm trying to get you guys to develop an intuition here. So let's see if we can sort of just reason out, just based on our sort of common knowledge or common sense, what the most likely shape or distribution would be. It's not a guarantee that that's the actual shape, but at least we can sort of have an intuition about it. So if we think about number of children in a U.S. household, well, if we think about what that might look like, right? What's the lowest amount that could happen? Well, there's certainly the possibility that there are going to be 0 children in a household. And of course, there's also, and that's maybe going to be pretty frequent. There's a lot of households that don't have any children in them. Now, we could argue about, are there more households that have a single child or 0 children? Who knows, right? But of course, having a single child might also be pretty common. Right? So those might be pretty similar in height. Because remember, the taller a bar is in a histogram, the more common that value of the variable is. Now, are there a lot of households with 2 children? For sure, right? And 2 children, also very common. 3 children, maybe still sort of common, but not as common. What about things like 4 or 5 or 6 children? Certainly they happen, but they get less and less frequent, right? There are some households that have 6 children. There's households that have 10 children, so on and so forth, but they're very uncommon. They're very rare. Now, are there houses that have -1 or -2 or -3 children? Not at all. So notice that there's very tall bars here and shorter ones here. That means that the number of children in a U.S. household is most likely right skewed. Low values, like 0, 1, 2, are very common. High values, like 5, 6, 7, 10, very uncommon, though they could happen. So that's exactly what we mean by a right skewed shape. Okay, let's talk about age of death in the United States. So for this one, same idea. If we just sort of are maybe making a guess, we might think that, maybe most common is going to be somewhere like 70 to 80. Now, are there a lot of people who live 80 to 90? Maybe there's some, right? Not a ton. Are there a lot of people who only live to like 60 to 70? That's also probably very large. Now, is there much else this way? Are there 90 to 100? Are there 100 to 110? Maybe a few, but if anything, it's going to be very small there. On this side, though, there is a lot of room still. People die in their 50s sometimes, 40s, 30s, 20s, so on. Now, does it happen commonly? Well, in a place like the US, a developed country, not too much, right? This is pretty infrequent, this is pretty infrequent, this is pretty infrequent, this is pretty infrequent. In other words, most people live into their 60s, 70s, 80s, somewhere in there. And a few people will die a lot earlier. So what this is saying is that this is most likely a left-skewed distribution. Now, would this be the same if we switched countries or if we switched time frames? Absolutely not, right? If we talked about like what was the age of death in the United States 200 years ago, we might not be able to make the same assumption. It's just the fact that nowadays, most people are living to an older age. There's really not many cases that people live beyond 90, 100, so on, but there are a few infrequent situations where people die a lot earlier than 60, 70, 80, so this would be a left-skewed distribution. Heights of adult males, well, we might not know exactly what the typical height is, but if we think about it, usually you hear somewhere that adult males typically are somewhere between 5'8", 5'9", on average, 68, 69 inches. So let's just say maybe 68 to 70 inches. So that's where a lot of people are. But if you think about it, there are certainly some people who are some adult males who are much taller than that. They don't happen that frequently, right? So you expect some pretty small bars this way. And same thing the other way. There are certainly some adult males that are much shorter than that, only 5'6", 5'4", 5'2", but again, they don't happen very frequently. So what are we sort of drawing there? Well, we're drawing something where there's a lot of frequency in the middle, and it's much less common on the two ends. So this is most likely Bell normal. Now, another way of thinking about this is that it is sort of equally shocking if we were like in a room of adult males, if an adult male who was 8 feet tall walked in, as it would be equally sort of shocking if an adult male who was only 4 feet tall walked in. You would sort of be like, wow, that person is very, very tall, that person is very, very short. Both are sort of rare, so there's tails going both ways. It's equally rare to be way above average as it is to be way below average in terms of height. All right. Finally, for ages of students in a public high school, what sort of is the most likely shape here? Well, if we think about the sort of common ages, there's probably 14 and 15, 16, 17, 18. Well, if you think about it, if you go through the school, there's going to be a lot of students in each of those ages because, well, those ages sort of represent the main grades, freshman, sophomore, junior, senior. So what we expect is, maybe there's a lot of 14 to 15-year-olds. Maybe there's slightly less 15 to 16-year-olds for some reason. Maybe more 16 to 17. Still a good amount of 17, 18. What we're saying is that there'd probably be about the same amount of 14 to 15-year-olds as 15 to 16-year-olds, 16 to 17, 17 to 18. In other words, we're talking about something that is most likely uniform. Now, I hope we can see why I sort of mentioned that uniform is pretty rare. If you think about it, it's only the fact that we're talking about students who are in this public high school, this system or structure that you go in at a certain age at and you leave at a certain age at. And of course, we replenish the student population each year. People who were freshmen become sophomores. People who were seniors leave and are no longer in the school. So it's sort of that artificial construct of the high school that's making this follow a uniform uniform distribution. If we looked at ages of people in the country, it is certainly not uniform. There's not the same amount of people who are 25 as there are people who are 95. So it's the fact that we're looking at this at a high school that makes it most likely uniform. Okay, so hopefully this gives you guys a little bit of a sense of why we care about shape. It's not just saying that the picture looks a certain way. It's really saying that there's a fundamental structure in our data. All right, let's wrap up this discussion with one more example of sort of taking a look at some data, running through the basic pieces of descriptive statistics we've done, as well as building one more histogram. All right. So for our last example here, let's suppose that there's a high school that wants to study how its students perform on the SAT math exam. So to study this, the school begins by breaking their students into two groups before the next SAT math exam. The first group is all the students that have never taken the exam before, and the second group is students who have taken the exam before. The school then randomly selects 7 students from each group, so 7 students who have never taken the exam before and 7 students who have taken the exam before, and they use those as their study. So this means that they get 14 data points, 7 who had never taken, 7 who had taken it before. So they get these 14 data points. So somebody scored a 330, somebody scored a 440, somebody scored all the way up to a 790. If you've taken the SAT math exam, you'll know that the scores range from 200 to 800, 200 being the lowest, 800 being the highest. All right, so let's go ahead and do our standard analysis. So we'll start by talking about population, sample, and individual. So population, sample, individual. What is our sample here? Well, we know that there were 14 data points. What were those 14 data points? Well, they were 14 students from this school. So our sample is 14 students from this high school. Well, what is that made out of? Well, that's made out of, in terms of individuals, 1 student from this high school. And the population would, of course, be all students from this high school. We are being specific of saying from this high school because, again, it specifically says here that the high school wants to study how their students perform on the SAT math exam. Not just students in general, but specifically ones that go to this school. All right, let's talk about the sampling technique that was used here. So what technique? So we notice that it mentions the word randomly in here. So again, that rules out convenience because convenience is not done randomly, and it rules out systematic because systematic uses a system instead of randomness. Now you will notice that it does say that they do an initial classification. They have 2 groups, students that have never taken the exam, students that have taken the exam, and they select 7 students from each. So in other words, they make sure that they get 7 students that have never taken it and 7 that have. That is stratification. There's an initial classification. So this is a stratified sample, and the strata are never taken and have taken. Okay? So there's 2 strata, all the students who have never taken the exam, all the students that have taken the exam. All right, let's calculate the mean and standard deviation. So again, this is a sample, so we'll be doing X bar and S. If you have your calculator, you can sort of follow along as we type this stuff in. So stat and edit, we can clear out everything from the sort of previous example. So we can go up to where it says L1 and put your cursor on there and then hit clear and enter. Then start typing this stuff in: 330, 440, 470, 500, 520, 520 again, 540, 580, 580, 630, 640, 670, 750, and 790. And notice again when we type in that 790, it says L1 of 14, so we know we've typed in 14 data points. Then we can hit stat, calc, and 1 var stats and calculate these things. Looks like the average here should come in as about 568.6. I'll only keep 1 decimal because this is in the hundreds. And the standard deviation with the sample standard deviation looks like it should be about 122.4. So the average score was 568.6 and the standard deviation was 122.4. The units, it might not be super clear here, but I guess it would be points in this situation because that's what we're talking about scores on a test, so points would be a good unit there. The average score was 568.6 points. The standard deviation was 122.4 points. All right, let's give that 5-number summary. Again, just sort of following off the calculator here. So we'll need the minimum, Q1, the median, Q3, and the maximum. So if we go down and we take a look at that, the minimum score was 330, Q1 was 500, then 560, then 640, and the maximum score was 790. And again, the units for all that would be in points. All right, last sort of basic bit of descriptive statistics, range and IQR. And then, of course, we'll go on to a separate page to finish up our diagram. So range here would be maximum minus minimum. So that would be 790 minus 330, which sounds like 460 points. And the IQR is Q3 minus Q1, so 640 minus 500, which is 140 points. Okay, so we've now done all the sort of basic measures that we've discussed thus far. Let's go ahead and give ourselves another page, and we'll go ahead and build our histogram. So for this, we'll need our classes and our frequencies. So notice that the problem tells us we should start from 300 with a class size of 100. So our first class will be 300, starting from 300, class size 100. So we'll go 100 units, that's 300 to 400. Remember, this will include 300, but exclude 400. Then we'll have 400 to 500. Always start the next one where the previous one ended. Then 500 to 600, 600 to 700, 700 to 800. Is that far enough? Can we just go up to 800? Yep, the highest score was 790, so they will land in here. Let's go ahead and count these, 300 to 400. So only this person, the 330, would fall in there. So the frequency would just be 1. Okay, so the frequency would just be 1 there. For 400 to 500, if we look at that, 400 to 500 would include these two, but it would not include the 500. So we would have this and this. There we go. I think I'll have a little bit of... Get rid of that. So, okay, there we go. Sorry, went back a little too far. There's 800, and yeah, okay. We did the first one. My apologies there. So frequency on the first guy was 1. And then for the second one, 400 to 500, like we said, we would not include the 500 because it does not include the right end. So there would only be 2 values there. Okay. For 500 to 600, we would include all of these. So I guess we would go all the way up to there. That looks like we have 1, 2, 3, 4, 5, 6. So we have 6 as a frequency there. For 600 to 700, we would include this, this, and this. So I guess we would go all the way up to there. Looks like a frequency of 3. And then 700 to 800, looks like we have 2 of them there. So that would give us a frequency of 2. We can again always do our quick check. If we sum those up, 1, 3, 9, 12, 14 does add up to our sample size of 14. Okay, let's go ahead and draw out our actual histogram then. This will be our frequency. We'll just label by 1. So 1, 2, 3, 4, 5, 6 this time. And then here, this will be our variable. So we can start 300, 400, 500, 600, 700, 800. Again, just make sure you go ahead and label your axis by the ends of those classes. You'll notice that I'm not worried about where this guy starts here because we're just interested in the lowest end of our variable there. You could actually put 300 here, but that is a little weird because normally if we have something at the origin there, we expect it to be at 0. So I would put the 300 a little scooted over and then start labeling the rest of your axis. All right, so our first one is height 1. So there we go. The next one is height 2. So there we go. Remember, all the bars should touch because where one interval ends, the next one begins. Then height 6. Then height 3. And then height 2. Okay, it's a little funky looking, but we got to try to give our best description for it. Now, the best description here would be that the shape is approximately Bell normal. No other shape would sort of make sense. It does look like we sort of have, if we imagine sort of a bell shape over it, right? Lots of people in the middle and then less people on both ends, both lower and higher than that. We said that if something was bell normal, another way to check it is that the mean and median should be pretty close. Let's go back and quickly check that. Notice our mean was 568, whereas our median was 560. Now, 568 and 560 are not exactly the same, but keep in mind we're in the numbers in the 500s. So this is like saying you have $568 versus $560. Those seem pretty close to each other given how large the numbers are. So that does seem to make sense to say that this thing is roughly symmetric, and since we visualized it, we can guess that the best description would be bell or normal here. All right, so this wraps up our first sort of visual display, which is a histogram. In our next video, we'll move on to the next major visual display for quantitative data, which is similar to a histogram, but it is called a stem and leaf plot. And we'll see, and we'll be able to sort of compare and contrast the advantages of these two displays.